Welcome. Now we are going to discuss gamma distribution, which is one of the continuous probability distributions. Okay. When do we make use of gamma distribution? When you try to model something which deals with the failure rate, or when you are dealing with some reliability testing, or when you perform some queuing theory operations. For these type of purposes, we make use of gamma distribution, and in most of the literature you can find that exponential distribution is used in the instances that I specified. The point to be noted is exponential distribution is a particular case of gamma distributions. So initially let us learn gamma distribution and see how it is changing to exponential distribution in the later part. Okay, so if x is set as a gamma random variable, then it must have this PDF, or if a random variable is having this uh, probability density function, then the corresponding random variable is known as gamma random variable. Okay, as I mentioned in one of the previous videos, whenever we study some new distribution, it is always better to derive the mean, variance and MGF by ourselves. Okay, so let us do that now. So we are going to calculate the moment generating function now, that is our MGF, which is denoted as M of t, which is nothing but what? Expectation of e to the power tx. And we know that uh, what is our f of x? Our f of x is 1 upon beta to the power alpha, gamma of alpha, and x to the power alpha minus 1 and e to the power minus x upon beta, where our alpha and beta are positive, and this is defined for x positive. Okay, when for other x's it is 0, that is obvious. And one more thing, what is gamma of alpha? Which is integral 0 to infinity x to the power alpha minus 1 e to the power minus x dx for some x, for some alpha positive. This is our gamma function. Now let us come back to the moment generating function m of t, which is defined as e to the power tx, that is integral which is defined from 0 to infinity e to the power tx, and our f of x is 1 upon beta to the power alpha, gamma of alpha, x to the power alpha minus 1 and e to the power minus x upon beta dx, isn't it? Okay, now here this beta to the power alpha and gamma of alpha are constant, so we take them outside. Integral 0 to infinity x to the power alpha minus 1, and here both are exponential to some power, right? So exponential of here what you have t, here 1 minus beta multiplied with x dx. So this one, let me rewrite it as minus of 1 upon beta minus t. Okay, so this is how we write it. So we just rewrite them, that's it. Now let me take some y to be, that is 1 upon beta minus t multiplied with x. Okay, so then what would be my dy? It is the same quantity 1 upon beta minus t dx, and in the place of dx, so what will we substitute? It is dy up on 1 upon beta minus t, isn't it? And here our x is varying from 0 to infinity. Okay, therefore our y will also vary from 0 to infinity. That is evident from this transformation. Okay, therefore our m of t will take the form integral 0 to infinity. From this, what you can very well write down the expression for x. So that is y upon 1 upon beta minus t whole power alpha, and this is y to the power alpha minus 1, and this is y to the power alpha minus 1, e to the power minus y, and this is dy upon 1 upon beta minus t to the power 1 itself. Now that the denominator quantity is a constant, so we take them outside. So 1 upon b to the power alpha gamma of alpha multiplied with 1 upon beta minus t to the power alpha, and 0 to infinity y to the power alpha minus 1 e to the power minus y dy. This is what we have. You just compare this one with the definition of gamma function. It is gamma of alpha, right? So what we have is 1 upon beta to the power alpha gamma of alpha 1 upon beta minus t to the power alpha, and this is gamma of alpha. So gamma of alpha and gamma of alpha gets cancelled. Now you can take this beta inside, so that your m of t is what? It is beta per alpha. Here also we have the per alpha, so it doesn't matter. Okay, so when you take this beta inside, it becomes 1 minus t beta to the power alpha. This is our moment generating function. Now if you differentiate it for the one time, you would end up with, okay, first it would be minus alpha upon 1 minus t beta to the power alpha plus 1 multiplied with minus beta. So it is alpha beta upon 1 minus t beta to the power alpha plus 1. In a similar way, if you differentiate it for the second time, you would end up with alpha beta square multiplied with alpha plus 1 divided by 1 minus t beta to the power alpha plus 2. Now that what is our mu? That is expectation of x, which is nothing but the derivative at 0 of this moment generating function. So at 0, what will we get? Alpha beta divided by 1 to the power alpha plus 1, which is alpha beta itself. Okay. And what is e to the power x square? Expectation of x square, that is second derivative at 0. Okay. So we will get alpha beta square alpha plus 1 upon 1. So this shall be written as alpha beta whole square plus alpha beta square. Okay. Our variance of x is expectation of x square minus mu square, which is alpha beta whole square plus alpha beta square minus alpha beta whole square, which is nothing but alpha beta square. Now that we have derived moment generating function, mean and variance. Now moving to the problem, as every distribution is prescribed using a set of parameters, x is said to be a gamma random variable with the parameters alpha and beta. So to represent some variate as a gamma variate, you need two parameters, namely alpha and beta, right? Okay, here some random variable follows gamma distribution with alpha and beta given. We are asked to find out the mean and variance, right? Okay, so here this beta means what? That is very important. So in some literature, they will have, okay, now let me come back here. Okay, instead of giving this in this form, in some literature they will prescribe your f of x as beta to the power alpha upon gamma alpha x to the power alpha minus 1 and e to the power minus beta x for x greater than 0 and alpha beta greater than 0. Okay, so this may be your gamma random variable has a PDF of this form, so it can take either of this form. Okay, now I think in this problem, in the solution, they are following the second form. When your beta is replaced with 1 upon beta, your mean would be what? Your mean would be alpha upon beta. Okay, and here it would be alpha upon beta square. It all depends on what PDF you are following. Okay, so here if here mean is given in this form and variance is given in this form. Suppose if you are using alpha beta thing, your mean would be what? Your mean would be 4. Okay, and your variance would be alpha beta square, that would be 8. Okay, whereas using this, what we get, it is alpha upon beta and alpha upon beta square. Here we just calculate the requirements and we find them out. Okay, remember, again I am repeating, your gamma distribution can be prescribed in any of these two forms. Okay, now you may ask me, what if simply alpha and beta is given, we don't know what to use? In that case, you just go with this one. Okay, that one, the one that I have written on the right hand side. So you just go this, proceed with this one. Sometimes if it is given, you just go with this one. Okay, but these two are valid density functions, you can very well verify that. That's it. Thank you.